Everyone, in this video we are going to cover the introductory part of Java and JVM architecture. So one of the famous things about Java is like it's been widely used. Why? Because of it's known as write once, run anywhere. It means like Vora. Once a code is written, it can be, once it's compiled, if it's a jar or a class file, it can be run in irrespective of the OS. Okay, for example, if I build it in the Windows, I can still run it on Mac or Linux environment. So let's see how this is being supported in Java. Before that, we also get to know about what is JDK, JRE, JVM and all. So JDK represents Java Development Kit, which is a superset of all these things. It's like when you want to write a code in Java, we require JDK in our machine, so that only we can like compile it and test those kind of things. Whereas JRE is not for compilation things. It's when we need to run our code in that environment, we require the corresponding JRE versions. Okay. Whereas the JVM comes, it's an internal working of Java, like how the memory will get allocated, how it's going to convert the code, how it's going to compile and execute, interpret things and all. Those kind of things will be handled inside JVM mesh. It's a Java virtual machine. So how we are supporting machine independent here is, once we compile the code using a JDK as a class file or a jar file, those files will be run on different machine. It needs to have the same JRE version. So for example, if I build it in the JRE version 1.8, when we run it in a different environment or different OS, that OS also needs the same JRE should be present there, so that only we can run our code. So through that JRE, it's been a machine independent part. Okay, so next we can go and discuss about the JVM architecture. JVM architecture is one of the most important whenever in the kind of interview or things. JVM is when they want to check your basic skills of Java, they will ask you the question from JVM part. So JVM gets split into three. One is the class loader, runtime data area, and then execution engine. Let's check about the class loader. In class loader, here you can see the class file. We will get the class file, and then it's been, so here in the JVM part, here we are having the .class file itself, because it's inside the JRE. JVM is present inside the JRE, so we already have the class file. Now we are going to see how that class file is going to be stored, processed, and execute. So that's what. So the class loader is, we are going to discuss how we are going to store it. This class file, or we also named as a bytecode, which has been generated. Okay, how we are going to process it in the class loader subsystem. Here it's been divided into three parts: loading, linking, and initialization. First, they are loading the code, and then they are linking it, and then they are initializing it. Loading itself has three parts: bootstrap, extension, and application. In bootstrap loading, we will load the important jar which is present. It's named as rt.jar. It will have all the basic APIs of object representation, class representation, variable things, and all these basic things will be defined in the rt.jar that will get loaded. Extension class loader, it's like here the libraries which is present inside the JRE lib folder will get loaded. And application class loader, this is the final part of where here our own application and its dependency will get loaded here only. Okay, our own application code, and then it's our own dependencies also get loaded in the application loading part. Linking is split into three parts: verify, prepare, and resolve. In verify, the bytecode which is being generated, it's going to verify whether the format is correct or not, the generated bytecode format is correct or not. In prepare, for the static variables, memory will get allocated. It will just allocate the memory. It's not going to update the values and all. It will just going to allocate it. Okay. Whereas in a resolve, all the symbolic memory reference will be replaced with the original value from the method area. In the method area, we used to have some symbolic memory reference that will be replaced with the original value. Initialization. Initialization is a final part of the class loader subsystem. Here we are going to assign the original value for that allocated static variable. If you remember, in prepare we are allocating the memory for it, whereas in initialization part only we are going to assign the original value, and it will start executing the static block. So whenever in Java the static void main will get executed. So this is how the initialization will assign the original value and start execution the static block. Okay, next comes the runtime data area. Runtime data area, while the code is being executed, how the memory be get allocated, assigned, and operation, how it's happening in backend. So let's see, runtime data area, we have two types of memory. One is a shared memory and another is a non-shared memory. The shared memory we also represent as a non-thread safe, because it's kind of a shared memory. It's not safer when we are doing a multi-threaded operation. Whereas non-shared memory, it's like for each thread it's going to allocate a separate memory for it. So in the let's think about like what and all in the shared memory, what and all areas. Like we have two type of areas. One is a method area and heap area. So method area, what we are going to store, this is method area and heap area is very important. So we need to know like what is being stored in the method area is like usually the static variables and all will get stored in the method area, whereas in the heap area it stores objects and its corresponding variables and all. Okay, whereas these method area and heap area, there will be only one method area and heap area in the entire JVM itself. Okay, so that's why it's kind of shared in the entire application, shared for the entire application. Okay, and next comes the non-shared memory, or let's say here we can all these other parts like stack area, PC register, native method stacks comes under non-shared memory, because for each thread it's going to allocate the different memory for inside it. Okay, so stack area, every thread a separate runtime stack will get created for every thread. You can see here like thread 1 to n. So for each thread it will going to create a separate runtime stack. In each runtime stack that we are going to represent a stack frame. For let's say when we call through a thread, there will be a multiple method. So what and all method is getting executed, finished, once it's completed, those kind of entries will be entered in the stack frame. So for example, thread 1 is started in this phase 1, phase 2, those kind of entries. Let's take phase 1, 2 and all, it's a method. Those kind of entries will be added in the stack frame. And then the stack frame also has other details also, like local variable array, operand stack, and frame data. Local variable array, when a method is being executed, there will be have a local variables and all inside the method. The scope of that variable is inside that method only. So that variables will be stored separately, because if a same method is being executed parallelly, the thread 1 will have a different value and thread 2 can also have some different value. So it should not impact, because of thread 2 is updating this value, it should not impact in thread 1. So that's why we have a local variable array. It stores all the local variable which is present in the method. And operand stack, the intermediate operation, the calculation, manipulation things which needs to be executed will be done in the operand stack. And next comes the frame data. In frame data we will have the symbols, and in case of exception, cache block will be stored here, like the stack trace things and all will get stored here. Okay, the next is a PC register. For each test we will have a separate PC register. What that PC register is like, it will have the current execution. For example, the thread 1 is executing this line number, this memory location, current execution, memory of the current execution will be stored here. The address of the current execution will get stored in this PC register. Once it's executed, let's say once it's executed, it will ask the PC register for the next instruction which just needs to be processed. Okay, and next comes the native method stack. It will hold the native method information. When we call the predefined Java APIs, some Java APIs and all inside it, they might have wrote in the native method kind of C++ way. So that's whenever we named as native, it will be not in Java, it will be from C++. Next comes the execution engine. Bytecode assigned to the runtime data area will be executed by the execution engine. Okay. it will read the bytecode and execute it. In the execution engine, we have the interpreter is a major role. It interprets the bytecode faster. It's like once the bytecode has been let's say the line interpreter, if it's trying to interpret the bytecode, it will interpret faster, but executing those, once it's interpreted to a native code, while it's executing, it will take a little longer. The execution will be slower than its interpretation. Okay, and that is a disadvantage with the interpreter. So it will interprets, if we are calling the same instruction or same kind of methods multiple times also, it will interpret every time. So this disadvantage, to overcome it, we have a JIT, it named as just-in-time compiler. What it's neutralizing the disadvantages which interpreter has. So what the just-in-time compiler will do is like, it will make a note of like this function is called how many times. Let's say if this particular function, if it's called multiple times, like more than 5 times or like that, then it will have a copy of it in the native method itself. It doesn't want to again to convert into an interpret again and then execute it. So it will have a copy of it, and when anytime it want to execute it, it will execute directly. It don't need to interpret it. Okay, so to do this operation, just-in-time compiler is being split into like intermediate code generator, code optimizer, target code generator, and profiler. So what the intermediate code generator will do is like, it will produce a intermediate code from the bytecode to the intermediate code, and then code optimizer, it will optimize whether it's able to optimize that intermediate code which is being generated. Target code generator, the producer, once it's been optimized, it will again convert it to a native code or machine level code which has been understood by the corresponding machine. And finally the profiler is the one, it's going to identify the hotspot in the sense how many times it's been going to be executed, how many times it's been reusing, those kind of things. Profiler will be make a note of it, so that the next time it's again want the same function, it don't needs to interpret, it's directly executed. And the garbage collection is also a bigger topic. Here in JVM architecture, let's have a small part of it, like a basic things about what the garbage collector will do. It's like it will collect and remove the unreferenced objects. So unreferenced in the sense, whenever the object becomes null, it means unreferenced. So those kind of objects will be removed from the memory itself. Okay, and we can also explicitly call the garbage collector by the code. It's like system.gc, using system.gc, but this is the execution is not guaranteed, because it's up to the JVM to take it up or not. We can call explicitly, but execution is not guaranteed. Okay, Java native interface, it will interact and provide the native libraries, whereas what native libraries will have is a collection of libraries required for the execution. Okay, and that's it. This is the entire JVM architecture. This is important. You just make sure, like, remember this diagram. With that diagram itself, it will be easier to explain things and all. Okay, thanks for watching.